Hello. Good morning, everyone. Uh, I'm Rahul. I'm a graduate student at Cal State Long Beach, and along with me, we have Dr. Amin and Dr. Awa, so who have a expertise in hardware security. So this talk is regarding like the utilization of property of chaos for post-quantum cryptography. I'll quickly walk you through the agenda. So initially we will discuss about like once we get the quantum computers, then what are the challenges encountered? And then we will also go through the existing quantum safe algorithms, which are in a kind of a competition with NIST. And then I will walk you through the property of chaos and how they can be one of the candidate for post-quantum cryptography. Along with that, I will also demonstrate like a few of the experiments we have done, like circuit implementation of the chaos-based cryptography. And then we will conclude and we will just have kind of a discussion that whether this is really suitable for using in the industry or still we have some kind of a challenges. Uh, let's begin with like trying to understand like what is post-quantum era. So right now we have like classical computers, which works usually in zeros and ones, which are deterministic. But with kind of like with the advent of and progress in quantum computers, we will be having a kind of very different property itself. So further the slides, I will just walk through. Just to begin with, uh, in cryptography, we are mainly dealing with symmetric and asymmetric cryptography. But before that, let's try to understand what is the foundation for asymmetric cryptography. So they are the mathematical foundation, which are the integer factorization and discrete logarithms. So till now, what makes them safe is like it's very difficult and time consuming for like performing the integer factorization and also discrete logs. So here we see the only limiting factor to break this particular method of cryptography is the time constraint, time and compute. Now like even we are seeing in the academia and also like few of the work done in industry that we have some kind of prototypes for quantum computers. So like what exactly are these quantum computers? It's good to begin with that. So quantum computers they use a property of kind of a qubits. So with these qubits, they have property of superimposition and entanglement. So using these property, they are quite good at doing certain kind of task, and they are not good at certain tasks. So for example, they are not good at sorting algorithms, but we are not concerned about that because from the previous slide, we were more focused about factorization, integer factorization, which quantum computers are quite very good at solving them. So, for example, like if we try to factor some very large prime number, then using a classical computer, it might take like billions of years, but the same can be achieved with quantum computers. Sorry, but the same can be achieved with quantum computer within like 4 to 5 hours. So if we see in the diagram, figure 2, so the left one shows that the time to break existing crypto system using classical computers, and the right one, it just shows how we can do with the quantum computer. So it is quite evident that with the advent and the progress in quantum computers, it will be quite easy to break the existing crypto systems. But, sorry.
Is that
Okay, so I will just reiterate the question. So the question was that on figure 2 on the right hand side, we have demonstrated that using quantum computers, the existing crypto system can be broken using logarithmic time. So to answer your question, so yeah, yeah. Okay. So now let's think this way, that theoretically we are proving that the quantum computers will break the existing crypto system. But now the question is, have we any evidence of proof that the existing crypto system has been broken or not? So even like yeah, fine. So now with the introduction of Shor's algorithm and Grover algorithm, so using their algorithm, if we just implement on quantum computers, it will be very easy to break the classical cryptography. And theoretically, it has been claimed that if we get a quantum computer, we can break the existing the mentioned crypto systems. Now, like as the community is already aware of the current problem statement, that down the line within like 20 year 30 year, we don't know the exact time duration when we will have a commercial quantum computers. So based on the thread, so there are like quantum safe algorithm being worked on, and like few of them I have mentioned here, but I'm not going into detail in any of them because that's not what I'm going to focus here. But still, like there's a huge interest in the academics and the industry where they try to kind of arrange competitions. For example, NIST, they have the competitions where we will be submitting our crypto algorithms, and the community will try to break them and just see whether that is safe or not. So there are other conferences also happening around, so where they just focus about the designing of the post-quantum cryptography. So, like as we have the data around, so we still need to protect it, not just right now with our classical crypto system, but also it should be like a resistant toward the quantum computer. For example, the data in the medical records. So, for example, there are few countries which require like storing the data for like 100 year, and few like for 5 year. So down the line, it is a necessity to just protect the data over the time. Now, one of the prime interest, like what is growing right now, is like the biomedical implantable devices. So now just imagine like there is some kind of a biomedical pacemaker which is implanted in a human being. Now, if that crypto system can be broken, then the attacker can have a control over it. And with the control, it's kind of a life-threatening situation. So, like this also gives kind of a reason why should be focusing on the quantum safe cryptography. Now, also, like there are other factors like financial institution where they are still using the old age uh, method of saving the data. For example, the tax systems where they store the data. Now, like although like there are existing methods which claim to be quantum safe, uh, we as a in academics we try to evaluate whether chaos can be one of the method for quantum safe cryptography. So like whenever we hear the word chaos, what just comes into our mind? So it's just kind of a randomness, disorder, maybe like what doesn't align to like generic pattern. So these all are kind of a like usually kind of a dictionary meaning of chaos. But chaos, which we use in like mathematics, is kind of a based on a few properties. So, like chaos has some property. So let's go through like these property. So this is one of the slide which will be like a foundation for how and why we can use the chaos for cryptography. Now, the first one is the deterministic. That chaos is one thing that it is always deterministic. It is always as a mathematical model. So now we have been given some equation. So the equation can be like a logistic equation and maybe like a differential equations. Now, the point is that whatever the value you feed to the equation, it will always be consistent. It won't change over time. Now, with the second property of chaos is nonlinear, that it will always be change. The variable will change with time. So this will apply for the property of differential equations. And maybe like we can also go for the higher order differential equations when it comes to like creating hyperchaotic maps. And the last one is the sensitive dependence. So this is one of the most important, like the property of chaos, which is used for designing the large key space. So we have heard about the butterfly effect, that if we change the initial condition in a very, very small amount, even delta, then the final outcome will be quite different. I mean, it won't be like approximated. It will be completely different from the previous delta. Okay. And by the way, like this chaos has already been applied for secret key cryptography, and also like the message encrypted from the pseudo-random number generator from a chaotic time series. And there are various ways we can just achieve this symmetric cryptography. Maybe like in chaos control, distributed dynamics encryption, chaotic cipher block. Let's see the first one, which.
Sorry, but it seems like you just described a pseudo-random number generator.
Yes.
Could you differentiate? Is there any differentiation?
Can you repeat the question for the recording?
Yeah, so the question was like we want to understand the difference between the pseudo-random number generator using chaotic system.
What's the difference between the chaos generator and the pseudo-random number generator?
Okay, so using chaos, like chaotic maps, we can generate pseudo-random number.
Is there any property of a pseudo-random number generator that exists today that does not meet them?
Okay, this.
What's new here? Okay.
Sorry, but feel free to repeat the question.
Okay. So the question was that like what's the difference between pseudo number generator and chaos, and how different is the generation of chaos from the pseudo number generator. So on a very high level, so it's like using these chaotic equations, we can generate the pseudo numbers. And we can also do a test of this pseudo number generator, whether we can perform like a statistical test as defined in the NIST, like the criteria. So based on that, we can just identify whether the numbers or the strings which are being generated from these equations. So these chaotic equations, we can design it ourselves. So we can have like a multiple chaotic equations. So we design this chaotic system, and we just generate the pseudo random numbers. And with the pseudo random number generated from this chaos, we just try to evaluate whether this is pseudo random number or not. So this is what we have done like earlier in few of our experiments. Is that fine?
I'm not hearing the difference. I do know what makes a pseudo-random number generator tick, so to speak. And a big part of it is the entropy which is fed to it in the first place.
Yeah.
And beyond that, it's deterministic and nonlinear, and it is quite a great deal of butterfly effect. And so how it would actually go building one is not clear to me yet. But I paged ahead and I didn't see it, but okay, I'll wait.
Okay. So for the deterministic, we can have like a discrete equations and differential equations. And with the differential equation, the very common is Lorentz system. Apart from that, we have Rosler system, Chua systems, but all the systems are based on what exactly we require. So, for example, like if we are seeking kind of a good performance and less compute intensive, then Chua system is not kind of a right choice to use it. So, based on our need, we can choose the particular equations. With the nonlinear, we'll just give an example of this logistic map. So on the right-hand side with figure 3, we just vary the value of the R, and we see that the graph is quite nonlinear. So with this property, we will design the keys. And the third one, the sensitive dependence. So like as I mentioned earlier in the slides, that if we change even the slight value of the initial condition of the equations, then the final outcome will be like so much of change. So for example, on the right hand side, so the first one is 0.1, and we make like a comparison by feeding the value to the equation using very slight variation like 0.101. Okay, so initially both the columns, so if we see, like initially this will be very much similar, I mean to say near about similar to the values, but when we go down, like we can think of it like a timeline. So as we are progressing towards the time, so initially they will be similar, but with the progress in the time, the initial, for example, 0.9, the last row, 0.9, and that will change it to 0.5. So this becomes kind of difficult for the attacker even to estimate that if we have system like this, and if this is the key, for example, the stream of secret key. So even if they know it, it will be difficult for them to estimate the final outcome. And on the left hand side, we see like a figure 4, which is kind of a generated graph from Chua equations. So that was generated using third order differential equation of Chua circuit. So one of the important property over there is that when we try to plot this graph from those 3 differential equations over the period of time, so we will receive 2 attractors. So attractors are something like if we see like the 2 circles on the left and the right, so they are the attractor. So the property is, I mean to say that the property what will happening over there is like the plot will just try to merge over that particular circles, but they are like very kind of near to each of the lines, but still they will not coincide. So that's one of the property of the attractor. So now when we evaluate using these chaotic equations for like designing crypto systems, then to make it more difficult for the attacker, we can have like a not just 2 scroll attractor, we can have like a 3 or even 4 scroll attractors. So designing how exactly we will be getting 3 or 4 scroll attractors, so those will be like defined by the equations, so which I have not covered here. Okay, so this is one of the slide where we try to kind of a distinguish between the existing cryptography system and when we try to translate it to a chaotic system. So the existing crypto system, like they are based on the finite integers, but for the chaotic one, they are real number. We can have, even with like the values between 2 and 3, we can have like a range of like a real number which we can use, like 2.1, 2.111, like that. We can have kind of a continuous value, and like I think few of the points I have already discussed. But now coming to the last distinction, which is the security and the performance. So the security and performance of the existing crypto algorithms are already well understood. But with chaotic systems, we are still to evaluate, and with the current information and in the academia, it's kind of they are lazy and their performance is not that good. And this is one of the chaotic system architecture which we use. So we have on the left hand side the encryption system, and the right hand side system where we decrypt it. And with this, we can see like a blurred, which is a logic locking. So this is what we propose in an existing chaotic system, that how exactly we will be using it with a logic locking. So logic locking is a mechanism using which the existing system, we can make some changes so that it is not visible to the attacker. And using that, we just try to send the data and receive it. And this is one of the practical realization of this Chua-based chaotic circuit. So on the figure 6, the left-hand side, which we see is on the upper top, that is kind of an encryption system, and the bottom one is a decryption. So if we see carefully, so on the left-hand side upper corner, that is R7, the register value 7. And on the similar to that, we have like a register 14. So like this is one of the way which we are proposing here, that even though like two systems like encryption and decryption, they have like I mean to say like they have to be identical, but we design the system in such a way that even though the keys are different, we are taking like a R7 and R14 as a key. So R7 value is 1.85 and R14 is 1.75. So we have designed in such a way using logic locking that like the message will still be decrypted. So on the right hand side, figure 7 and 8. So here we are showing the single scroll attractor, and like as we saw earlier, like a double scroll attractor. So these values are some kind of like based on the mathematical equations, we can just obtain it. And if you see like on the figure 9, we have the red, we have this red is like a plain text. We are sending kind of over here like a pulse signal. And the blue one, it is like with chaos. So with this particular circuit, we are just extending it and just showing it over here. So the same figure 10 on the right hand side, if we see, so over there we are sending a pulse signal, like a binary pulse. And then after we are infusing that with the chaos, which is generated using the particular circuit. and then we are just receiving it. So the particular figure 11, they just explain the red one. If we see, it is the binary signals, and the ever blue one, it is like the same data binary infused with chaos. And like on figure 12, we just try to decode it, and we see, like, although it will not decode it exactly the same, so it is just because of the synchronization issue. So this is expected, like this happens, but this is where like a post-processing technique comes into the picture, where we take the decoded message from the chaos and we try to kind of put an offset, and based on that we just try to obtain the earlier message. So one of the property over here is that, for example, that even if we are just creating a let's translate this particular diagram as a transmitter and a receiver. So even if have a transmitter and kind of a receiver, so over there, if the attacker can get all the details of the transmitter and can also replicate it. But this is where the logic locking comes into the picture, that even if the attacker gets all the information, that what are the equations, what are the initial values which are being fed in the encryption system, even then he won't be able to decode it. So let's move to the implementation challenge. So one of the biggest implementation challenge is like how exactly we are going to define a key which will show kind of a non-chaotic behavior. So we can do some kind of a pseudo random number test, or something like a predefined, but still it's kind of a challenge. Now another is like the existing keys, so they are sensitive to the secret, they have a low sensitivity to the secret key. So for example, like there was a submission in NIST for this post-quantum crypto system algorithms. So over there was an algorithm, RVB algorithm. So that was also based on a chaotic map. That was in the round 1 of the submission back in 2018. So like when they designed this, when they designed the crypto system using this chaos-based chaotic map, the thing was that although during the time of a submission it was received well, but within like a few days only, it was already broken using lattice-based algorithm. So one of the reason what we observed there was that it has a low key space. So they have used, I think, some chaotic map, which I don't remember right now. So I mean to say, like over here, just re-emphasize that the chaotic based system, they have been used for crypto systems. Now there are some kind of a design rule which should be followed, that once we design an existing crypto system, that should not only be taken from a viewpoint that is kind of a post-quantum attack secure, but we should also see like whether that can be broken down using the application specific attack. And particular to that, selection of the chaotic map with sensitivity to control parameter mismatch is also one of the key factor where we need to focus. Now, like we just, so till now we just explored with some examples and experimental results that how chaotic systems can be used for cryptography, which we claim which are which are resistant to quantum attacks. Uh, but still, let's see the industrial adoption. So recently, like few months ago, like there was a publication result from NIST, where they announced the results that this lattice-based and hash-based function, they were the winners, and where it was used for like public key encryption, one algorithm, and three of them were for digital signature. And also like in industry, for example, IBM, Microsoft. So there are some of the projects which are going on for quantum safe algorithms. And also, for example, like Microsoft, they have quantum safe tapes, um, which is already implemented. So like with this, I will just conclude that we understood the properties of this this chaos-based cryptography, and based on this property, we designed the chaotic uh, cryptology. And apart from that, we also saw few of the challenges while implementing the post-quantum cryptography. Uh, but to be very clear, I mean to say like there is no silver bullet for any of the crypto algorithms. I mean to say like it's always up to like the compute power and the time and kind of the algorithm which we are implementing. But still, with the growing industry adaptation, we are still to claim whether chaos-based cryptography can still be used or not. So over here, the claim is not kind of claiming that using chaos we can have a quantum safe algorithm. This is kind of a growing interest over in the academia. So the overall motive was to just create a awareness, and recently, there are few of the academic publications where they claim that they can make a secure exchange of the keys using chaos-based systems. And they also do a attack analysis where they claim that it is even like it can't be broken by the quantum computers. But again, the point is like that is all theoretical. We still need to implement it like a code-based implementation, hardware-based implementation, and still we need to evaluate it whether that is working or not. So with this, I will just conclude my talk. Thank you, everyone. Uh, I'm just open for questions.
An observation. The slides that are posted don't match your slides that you showed, so we need to just get a new copy.
Okay, I will just share.
I think we had a previous mission.
Yeah,
I think the new slides are much clearer.
Yes.
Okay.
Some of this is previous. Thanks.
thank you. Okay, so if there are no questions, thank you, everyone.